All right, let's get started quickly. Today, I'm going to be talking about uh, the GPU specifically. So far, we've put together the model. I think the base model is ready in the sense that you can look at all the parts of a transformer and we understand how to put together a transformer, both the encoder and the decoder. Now, this little piece that I'm going to be talking about is so that, as we go into the next few, you know, streams, we need to understand how you schedule work that is, you know, executed by the GPU. That means how do you get the GPU to do some work for you? All right. And since my machine is an Apple machine, I'm pretty much going to talk about that. But Candle, the ML framework that we are using, actually provides, obviously, like every other framework, the whole idea of a framework is they provide abstractions over multiple different kinds of GPUs. Right now, we're only talking about three, abstractions. I'll talk about that. You can run your stuff on the CPU. You can run your stuff on Apple's GPUs, which is anything that Apple provides, which has got the metal back, which uses Apple's metal API. The second one is NVIDIA's GPUs, obviously, which pretty much is leveraging CUDA to program their GPUs. So those are the three backends that we've got. Today we're going to be talking about how do you dispatch kernels using the Candle framework. Now this is applicable, most of what we will cover is applicable across. That is you for any of the three backends because it's an abstraction that I'm going to be covering. So we'll just talk about those pieces first, and then in the next stream, I don't want this to be too long, so we'll talk about you know the compute graph that's actually generated at the at the end of your putting together your model. What does that look like? And we'll get to the part of back propagation and how that is specifically implemented in Candle. It's not a whole lot of rocket science. I think I finally got to understand how that works. So we'll cover that as well. But before we get there, let's at least understand what is a kernel, which is nothing but, some piece of code that you're going to write that's going to directly run on your GPU. And GPUs are parallel machines in the sense that they do a lot of parallel computing. Let's take a quick look at, how Apple describes this. So uh, Apple says pretty much the way you work with their GPUs, if you're using Metal specifically, is you have this client server kind of a model where your application is the client and the GPU is the server. So you issue commands to the server and the server responds. That's pretty much how you want to go through. I mean, you want to think about it. Uh, but there's a bunch of things that actually happen. All right. So before you can get into this client server model, you need to set up some resources, what's called the command structure. That means how are you going to issue these commands? So, and what is the thing sitting on the GPU that's actually processing these commands? So effectively, we need to set those things up. And this page really lays it out well. It's direct documentation from Apple. So you set up something called a command queue into which you insert your command buffers, and those command buffers in turn contain your actual commands. It sort of looks something like this: your command queue, your buffers, and your commands. And once that's done, you submit this, work, the commands, uh, to your GPU. So you remember I was talking about kernels? That's the piece of code. It's actually a function or a piece of code that is going to be executed on your GPU by all of your GPU cores. Not all of them, depending on how you've written it. So what wraps this kernel function is something called a pipeline object, and you can have different kinds of pipeline objects. Stuff for graphics, where you do rendering, stuff for compute, which is what we're interested in. So just let's just put that at the high level. We don't want to get deep into the GPU's hardware architecture and figure out, what's actually happening there. That's not what we're going to be covering. But in any case, the idea is we simply create a command buffer. We create a command queue, or we get an instance for the command queue, create a command buffers, and then start encoding commands into the command buffer. So all these different objects that are required to set up the command structure is what we need to put together, and then that's so that we're able to submit work to Apple's GPU. Now, the reason I wanted to figure this out is because this is sort of important for you to understand how Candle's ML framework actually works under the hood. This is strictly not necessary if you're simply going ahead and just putting together a model and doing some training and all of that. You don't really need to worry about all of this. But I'm interested in this because, we're talking about the scenarios that I'll be working with, where we're talking about AI that's probably running on, or models that are going to be running on devices that are much smaller. Let's say a phone in our case, or something like that. Like if you take in case of metal, that's pretty much the only thing that we'll be targeting. That's constrained in any way, because when you talk about Apple's computers, etc., they're pretty good. But getting to know this is a good way to learn how these things are built, because you can adapt some of this work for, other kinds of hardware where you may need to think about a lot of optimization for your stuff to work. That part I'll get to later on, but let's just focus on getting this together. So you do all of this stuff and then you get, you submit work and you're done. But how does this actually work in Candle? Let's actually look at how it works. So what I've done here is I've put together a very simple, yeah, demonstrator, in the sense it's a basic unit test. To you just want to see how a matrix multiplication works, right? But my interest is not the matrix multiplication. My interest is when I write this piece of code, this is written in Rust. Obviously, that's not going to be executed on the GPU. You want to know what happens, throughout that process. That's that this work of actually doing the matrix multiplication between something called the tensor A and tensor B. How does that work actually happen on the GPU? All right, and how does Candle help us do that? So let's look at it this way. The first thing that you see is I've made some notes so that you can follow along. Candle uses an abstraction. All frameworks, that's what they do. They provide abstraction so that you don't build all of this stuff. That's why you should be sticking with frameworks, unless you want to do something that's completely hotke and you don't know, uh, there's no framework that supports your use case. But in any case, so Candle has an abstraction called storage, which I will get to. Storage is just an enum. Uh, the, Essentially, that represents the data store. That means every tensor is backed by some storage. And as I said, the storage can be of one of three types: CPU storage, CUDA storage, or metal storage. The names are pretty self-explanatory. CPU is something that you're using this. You're basically going to work with the CPU alone. CUDA is for NVIDIA, metal is for Apple's GPUs. Now, when we invoke an operation such as matmul, which is matrix multiplication, we end up calling the underlying storage implementations that implementation of matmul, right? In the case of Apple, that's metal storage. I'll walk you through what that looks like. We're going to be doing something like setting up all the GPU resources that I was referring to previously, like the buffers, the command buffers, the command and sorry, the command queue and all of that stuff. We're going to get handles to all of that. And then finally, we end up calling some function in this crate called, let me just highlight that, the candle metal kernels crate. This is actually a crate that does the final step of uh, bundling your work and pushing it off to the GPU. And I'm not going to get into the actual kernels that are written, because that's not Rust at all. Firstly, secondly, for Apple, that's using a language called metal shading language. It's nothing but a variant of C++. With some extra additions to it. If you're really interested in that, I would recommend watching my other stream where I actually talked about this in, where's that? Wait, So there's another stream. Oh, wait. So you could pretty much look up my other stream where I talk about metal. Uh, it's MTL. So this is basically a sort of a playground that I try to put together where I was trying to just understand how, you know, Apple's Metal API works, and it's a very thin layer that's put together. So you can probably look at this. It's very well, I'd say, at least for a beginner, an absolute beginner, this is easy to understand how you can use the Metal RS crate, which is nothing but a wrapper around its bindings for the Objective-C, or the Objective-C implementation that you have, which provides access to Apple's Metal APIs. Yeah. So if you just look at this, you will see that, you've got different versions of matrix multiplications that I've written, uh, where you see all the Rust code is here, but then you'll start to see stuff like, you know, create the device, get a command queue, all of this. Finally, at the end, you will see that, we set up our threads per grid, and then we dispatch that kernel, which is the dispatch threads. The moment we call commit, that's when you're submitting work to the queue, and then the GPU takes over. You no longer have any idea when that work's going to complete. That's not your problem. So yeah, you can look at this particular what do you say, playground project, where you can look at how basically we get to deploy a kernel on Apple's GPUs. All right, that's one. But now let's get back to uh, the candle way of doing things. So if you see here, when I jump into matmul, which is the tensor implementation of matmul, it does a bunch of checks depending on the dimensions that you have to do, because you can't just do matrix multiplication randomly. You have this thing called storage. This is going to return the underlying storage. Let's look at that underlying storage type for a bit first. As you can see, this is our storage abstraction, right? We can have either one is 3 and metal is 1. And if you look at the metal storage backend, you see it's pretty straightforward. Now, most of the stuff over here, for example, what you see over here, buffer, this is not a Rust type, actually. It's a Rust wrapper around something like an Objective-C type. Not important, but just so that you understand how things are working under the hood. Same thing over here. Metal device is again an abstraction that Candle provides, but um, it actually wraps the actual underlying logical representation of a GPU, which is device. Uh, Again, this is actually a wrapper around a foreign type. But anyway, all of this stuff is neatly wrapped in things that make it safer to use. And you will see pervasive use of this particular pattern in Candle. We have an arc with a read-write lock, right? So the arc gives you multiple ownership, and the read-write lock gives you uh, mutation, but you also give you multiple read access. In any case, all of this stuff is just setting up the the types that you need in order for you to interact with the GPU, or rather work with the GPU. Okay, so this is the metal storage abstraction I was talking about. Let's get back to the actual implementation. So we basically pull in the metal storage backend, and then we call that implementation of matmul, which takes us here. So if you just take a look at this, the implementation says, okay, I'm not interested in CPU, I'm not interested in GPU, I'm interested in metal. Let's just take a look at that. The matmul implementation of the underlying storage says, okay, here's the implementation. So this is the implementation of matmul for this particular storage. Now, you should immediately see that there's a lot of stuff happening. This is where we're setting up some of the GPU resources that we need. We're setting up the command structure, rather, to be very precise. And we are attempting to finally call this particular function, all right? And this function is basically part of what is called Candle Metal Kernels crate. I believe these are all freestanding functions. Yeah, these are all freestanding functions. wherein you call them uh, once you've set up your resources, and then it does the rest. There's a whole lot of checks that happen because you want to be safe, obviously, and you want to do the right thing. And you also want to make sure that your results are accurate. So there's quite a bit of type checking that happens over here. Whether the matrix that you provided is contiguously laid out in memory, not contiguously laid out in memory. We also want some optimizations with constants. Then there's some SIMD work. Well, that's fine. This is just, trying to write the best possible kernel that you could. In any case, then finally, we get to the last part, which is we have, we've created the command buffer saying, okay, go do a matrix multiplication operation. We're going to encode, this uh, matrix multiplication kernel into the command buffer. And that's what's happening over here, right? We're setting the compute pipeline stage, and then we're setting how many threads or how many cores, not cores, but how many threads do we need to get this work done. Then the three buffers represent three, the three different matrices in this case, which is the tensor A, B, and then the product of that, which is C. And then lastly, the important thing is we get to this part where we say end encoding. Now, the thing that stumped me for quite some time is it's interesting that you're setting up all the work, but you're never really committing that work or submitting that work to the command queue. That's the biggest question I had. And I ran around quite a bit to figure out where this is happening. Sometimes you just don't know where this is happening. But I finally realized that, I missed a very small detail. So I'll just talk about that as well. But I hope this makes sense. This is how Candle provides that abstraction wherein the different backends, you have a different implementation that kicks in. And then you can follow the steps for each backend and say, okay, here's how you want to submit work for CUDA, here's how you want to submit work for Metal, and then the CPU. It's a nice little abstraction. It's very straightforward, actually. There's not too many layers upon layers, and that's the thing I like about this framework. It's actually, yeah, some good design choices. I would say that much. People generally underestimate the power of simplicity, and I think this is actually simpler. Although you might still think that just there's too many uh, there's too many functions you seem to keep jumping to. That's not. Let me just say that. Anyway, so let me get to this part where we talk about this encoding. So finally, essentially, we call uh, the generalized matrix multiplication call, which is what we need in order to actually push work. But even at this point, when we call this function, we're not really submitting work. We've put up all the resources, we've got the kernel, etc., in our pipeline object, all that's done, but we've not really submitted this work into the command queue. In order for you to submit that work into the command queue, you need to do something. You need to actually call the final call, which I showed you here, where this is it. Without this, you're never going to get the work done, right? So what's actually happening here is the interesting thing is um, Candle actually has a lazy implementation. We don't want to submit command buffer, like every command buffer that you get, you just submit that and then let the GPU done. You want to saturate the GPU with as much work as you think is meaningful. So we want 50 commands, and then we want the GPU to work on 50 commands. That's kind of what happens here. So if you see closely, let me go back to the initial implementation. So if you see here, when you create the device and then set up some of the resources, there is an actual implementation that says, tell me if this is, we've got 50 compute uh, commands per buffer. All right. If you've got that, then go ahead and call the commit. Go ahead and commit this buffer. The logic over here is actually in our implementation for tensors. We can go ahead and quickly see them. Let me try and see if I can show you that. So And wait, jump around. So I actually asked this question on the command on the candle discussions page itself, and you know, I was helped. That was good, and I was finally able to make it to the answer as well. So you'll find that there's an implementation for command buffers. I believe this is part of the let me see. Okay, yeah, this is part of the metal storage itself. So if I just click on metal device and come down and look at, how this thing implements, what is that? Yeah, the command buffer, you will see that the implementation pretty much says, check if you've got 50 commands with you. If you do, that's what this is saying. If you've got this, then call the command buffer command. That's great. In our case, what stumped me was, okay, only if I have 50 commands, that's going to work. Obviously, my matrix multiplication is just one single operation. That's not going to really trigger this logic. So how does this work? Uh, what happened was this implementation, there's a slight difference. You can actually look at the display implementation. So when you actually display or when you actually call a result, that means you want to print the contents of result, then you automatically submit work. So there's the lazy implementation and candle simply means two things. Work, or rather, I'll actually explain this pretty well over here. So commands that are encoded in a command buffer are only committed when one of these two conditions are met. Either you obviously exceed that 50 commands per buffer threshold, or you end up indirectly triggering a commit, such as printing the actual data of a tensor. That's why this is a lazy implementation, as I'm saying, which means uh, I'm not going to try to follow through and say exactly how does printing work, but you can go ahead and look at that here. So we implement the display trait here. And then if you just go through this implementation, you'll be able to see that very quickly. For example, where's F32? You'd be able to see that we are actually calling format tensor. And now you go look at format tensor, you'll see that you actually end up calling commit at the end of it. That's why you'd be able to get the result of this. Okay. So when you're printing the result, and when you're doing some indirect operation that's manually triggering a commit, is through some of these operations. Specifically, when you want to display something, it's an indirect operation. So the implementation is certainly lazy, and that was a little I had to run around a bit. But yeah, I think right now what I wanted to cover was this much. Just understanding, this piece. That's it. How do we actually get, if we are using the metal backend and we are performing a matrix multiplication, how does Candle actually submit work to the GPU and get the results back, right? So as you can see, there's an abstraction called storage, and that storage abstraction tells you, you can either have one of three backends, and then you call the implementation for one of these three backends, and then you do the respective things that you need for these three different backends to get your result back. Also, the implementation is lazy in the sense that it's a very good thing. You don't want to simply, uh, you know, submit a single command and then, get a response for that. It makes no sense. When you're working with GPUs, you obviously you want more throughput. So you take advantage of pushing out more work and getting that work done in parallel, getting a response back. And yeah, you can obviously take a look at this, look at my previous repo that I mentioned, which is this particular one, because this explains in some detail, you know, when you use the GPU, what kind of speed ups do you get when you compare it with the CPU, when you compare it with a parallelized version of the CPU, etc. So, I and plus it sort of is much simpler to understand how you work with the Metal API here because it's very direct. Rather, there's a lot of work happening because this is a framework in Candle. All right, so this is what I wanted to cover in Candle, and I've also got the links over there that you can probably go through. The other thing that I didn't mention is, this thing called flash attention kernels. This is so basically I mentioned that, the if you actually go and look at, let me see if I can do this. So if you actually go and look at the actual Candle, uh, the Candle framework, the actual source code of it, you'll find that there is a place where you can find uh, these actual metal files, all right? So this stuff, this is your actual, let me see if I can find, you're not able to see this particular, metal file. The reason is because we're actually using, somebody's written uh, this, uh, somebody's written some metal kernels and have already compiled them, and we're using the compiled artifacts rather than, us compiling them and then using that. And this is pretty fast, and this is open source. Somebody wrote all of this in Swift, apparently. And that's the metal attention, flash attention kernels. Any case, so you can actually see that pretty much looks like C++, which I definitely do not like. I wish. And I think at some point, we can figure out how we can write all of this in Rust, the kernels itself. Obviously, I don't know if you need support from Apple, or we can do this step by step. There's going to be some amount of compiler engineering involved over here because Apple produces uh, a lot of intermediate formats like AIR and MetalLib and stuff like that, which is another word. They're just, you know, I think they're LLVM IR, but with some additions, I think. But in any case, we probably need to do a lot of compiler engineering work to say you want to support something like Rust over here. Um, it's an interesting view, and yeah, we can sort of think about it. But yeah, this stuff is what you get that we can use. This is a typical metal file, so that's what you get. This is the stuff that actually runs on the GPU. You don't write this in Rust. You write this in whatever metal shaping language that Rust provides, sorry, Apple provides. It's got additional, attributes such as these attributes and stuff. That's the difference, I think. Anyway, so that's pretty much um, the piece that I wanted to cover for dispatching kernels, how GPU kernels are dispatched using Candle, and we've taken the example of Metal itself. Uh, the same thing applies for CUDA. If you were interested in CUDA, you can pretty much think along the same lines. But I think the way you set up the GPU is a little different because, CUDA uses a single source file. Um, but I guess it's mostly the same, I presume. Yeah. Okay, so that's about it for this one. The next thing, what we can talk about is, I've got another, this is already working, you can take a look at this. We actually will be able to take a look at all of the different operations that will be performed in our entire transformer. That means we have the encoder, and the encoder tensors keep flowing through. So there's a matrix multiplication, there's a transpose operation, there is a broadcast operation. All of this stuff, the way all these operations are glued together, we can actually take a look at that. I don't have a visual way of showing you that, but I'll just, for simplicity's sake, I can show you what happens when you do something like uh, so okay, what did I miss? Sorry, get up, grab. All right. Oh, sorry, wrong. So you'd see this. So you'd see that, you know, this is the leaf node. Uh, Assume that, you've got tensors and nodes, and then the leaf node tensors are the inputs to one operation that produces another output. So you'd be able to build a graph like this, and this is what your compute graph is. This is something that you need before you can do the backpropagation. We'll cover this part in the next stream. All right? It's interesting. The way it's implemented is what we're interested in, because all of this is already done. Again, I want to say this. I think I've said this enough in the previous streams. The fundamentals of this, we're not interested in how Candle is doing, how Candle is implementing stuff, so that uh, we learn more about Candle and Rust in the process. Okay, that's it. Have a good day.